Okay, so now since we have this representation for the antiderivative of e to the minus x squared as a power series centered at 0, let us do something interesting to it. So let's pick f of x, the antiderivative of e to the minus x squared dx, with the initial condition f of 0 equals 0. So it's not hard to check that it means that in the above series, c equals 0. So we have the representation f of x equals the antiderivative equals k from 0 to infinity minus 1 to the k x to the 2k plus 1 over 2k plus 1 times k factorial. So let's see how well we can approximate this function with polynomials. So we have, say, let's say t1. Let's start with t0 actually. So t0 is going to be a linear, is going to be a constant, and so since we have that f of 0 is 0, t0 of x must be 0 as well. So it's the constant polynomial approximation. So note that the indexing is a little bit off here, because if we set k equals 0 into the series, we get nonetheless a linear term. So that's because so this indexing here is over odd powers, and when we say Tn of x, we mean the nth degree polynomial, and so that is why, even though when you plug in k equals 0 into the series, you get linear term, we are saying that t0 is 0. It's the constant that approximates our function at 0, which of course must be 0. We'll see a picture to illustrate this fact. So then t1 of x, for example, is the linear polynomial. It's the following expression. It's minus 1 to the 0, so it corresponds to the value of the index k 0 here. So we have minus 1 to the 0, x to the first divided by 1 times 0 factorial, so that is just x. t2, we won't have a t2 because so this only goes over the odd powers of x. So then t3 of x is the degree 3 polynomial, and we'll get it by summing up the above series for k equals 1 and k equals for k equals 0 and k equals 1, sorry. We have the sum from k equals 0 to k equals 1 of this expression, x to the 2k plus 1 divided by 2k plus 1 k factorial, and so that gives us x plus for k equal 1 I get minus 1, so that's minus x to the third divided by 2 plus 1 divided by 3, and k factorial in this case is 1 factorial, and so that gives me this polynomial here. Similarly, there is no t4 because the right hand side only contains odd powers, but there is t5, and so that gives me the sum from k equals 0 to 2 minus 1 to the k, x to the 2k plus 1 over 2k plus 1 times k factorial. So that's x minus x cubed over 3. That's the first two terms I have here from t3. And then for the fifth degree term, I will have the value of k equal to 2. And so that gives me -1 to the 2, so that's +1, x to the 5th, +1 times x to the 5th, divided by 5 times 2 factorial, so that would be 10 here in denominator. And so this is the degree 5 polynomial that approximates f of x at 0. And let's do one more. Let's write down t7, and so that will be the k from 0 to 3 minus, well, we'll get the same formula, so let's just skip the formula. And the new term that we'll get is as follows. We have these 3 terms, and then we'll have minus x to the 7th, because we have 2 times 3, because the value for k will be 3. We'll have x to the 7th over 7 times 3 factorial, because we'll have the highest value for k will be 3, so that's 7 times 3 factorial, which is 6. And so this finally gives us the polynomial of this form. And so if we now plot these polynomials next to the function, the antiderivative. So here I have in red, this is my f of x. So this is the antiderivative of e to the minus x squared, and so on. And here I have the plots of all of my polynomials. So you see that the darker the color here is, the higher the degree of a polynomial. So first there is the constant polynomial, which is just 0, which we cannot see because it coincides with the x-axis. Then there is the linear polynomial, which we obtained as t1 of x, which was just x, and so you can see it over here. So it's in this light blue color, and so this is our polynomial x. And then now we have the third degree polynomial, which is in this slightly darker blue. So it also has negative leading order terms. So that would be this guy. So this is the minus x cubed over 3 plus x. So you see that it approximates the red function slightly better. So whereas the light blue x just went by our function, this slightly darker blue x cubed will follow it a little bit closer, like so. Then we have the fifth degree polynomial, which we obtained right here. So that's x minus x cubed over 3 plus x to the 5th over 10, exactly as we have over here. And it's this darker colored graph over here. So this is the x minus x cubed over 3 plus x to the 5th over 10, as we had here. And so it approximates the red graph even better. And finally, there is the 7th degree T7 shown here in this very dark blue here. And this is the T7, the equation for which you have here and also here. And so this is the T7 of x. So you see that as the degree of the Taylor polynomial increases, you get better and better approximations for the function f of x. And so indeed, if we were to compute the error of this approximation using the Taylor's inequality, so let's use Taylor's inequality, which says that f of x minus Tn of x is at most m over n plus 1 factorial times x minus x minus 0 in our case to the n plus 1. So you see that as the degree of the polynomial n increases, the right hand side gets smaller and smaller. So assuming that the derivative of f, the derivatives of f do not grow very fast. So in our case, we have m is a constant such that the next order derivative of f is bounded by this constant. And so you can, in principle, explicitly compute all these constants because you know what the derivative of f is, right? It's written right here. Derivative of f is e to the minus x squared, and then you get subsequent derivatives by differentiating e to the minus x squared a couple more times. So that will give you the explicit constants here for to put in the right hand side to get m here, and then you'll get estimates for how far the polynomial t sub n deviates from the true value of the function. But even from these graphs, you can see that the higher the power of the polynomial, the closer your polynomial follows the red graph of the function. And so I will stop here. I will leave the explicit computations to you as an exercise. So as an exercise, compute the derivatives of f to the order, say, 8, for example. So that's probably a little bit tedious. So let's say compute f1 and f, let's say, so we'll have to estimate the linear approximation and the cubic approximation. We'll need f2 and f4. So compute these as an exercise and find explicit values for m. To complete the discussion of approximating functions with Taylor polynomials, let me just mention that the graphs we had over here, where we plotted the function as well as its Taylor polynomials at a fixed point, in this case 0. So these were effectively the Maclaurin polynomials. So these graphs were produced using a short Python routine, which can be found online. So if you go to this web page, you'll find some discussion for how to produce such graphs. So you will find the code of the routine that produces them. So it is the Taylor plot routine over here. And the way it works is it takes the function, in this case the Bessel function J0. It takes a function, it takes the order of Taylor polynomial, the maximal order of the Taylor polynomial that you want to use, as well as a range for x, and then it will plot the function in red as well as its polynomials up to the degree that you have indicated on the interval from minus, say, 10 in this case, up to 10. And so the degree of the polynomial will be shown in the lightness of the color. So that the darker the color here, the higher the degree of the polynomial. And so you can play with this code to produce some other graphs as well. And so I recommend that if you're interested in how these graphs are produced, that you go to this web page and read through the code. It's fairly short code. It's effectively just 2 screenfuls of code right here, and it's written in Python, so it's fairly readable. It's almost plain English right there. And so this completes our discussion of approximating functions with Taylor polynomials so far.